Thank you very much for the introduction. Thank you very much also the organizers, especially Andrea Mogliardi, who sent me the invitation. It's an honor and a pleasure to be here today. And yes, I'm going to talk to you about one type of optoelectronic devices that have become very relevant nowadays for the control of light in many different optical systems, and in particular for systems in many biological devices are being used in many extremely interesting applications. As said, I'm coming from the city of Elche, where it's in the south of the Valencian region in Spain, where this quite recent university, nothing to do with this great old university that you have here. We are only 30 years old. It's the last public university open in Spain. And yes, we are developing there our laboratory. Okay, this is the outline I'm going to follow. I will talk you a little bit about liquid crystal displays and spatial light modulators. I'll give you some of the examples that we have been doing in our lab and applications in diffractive optics, interferometry, polarization control, and spectral control. And if I have time, I will conclude also with some examples of liquid crystal geometric phase diffractive elements. Okay, liquid crystal devices. This is something I'm sure you are all familiar with. We have liquid crystal displays for many years now. You can find them in all types of screens, in telephones, in computers, in flat panels. This has been for years now in the market. Although the history of liquid crystals is quite old, the first to recognize the liquid crystal state was this person here, Friedrich Renitzer, who, working with a polarizing microscope, could see this kind of images you are seeing here, these colors that we observe in certain materials when we look at them between cross polarizers. These are named as birefringence colors, and they appear when the sample we are looking at, it's birefringent. That means that it's showing, instead of the usual case that you're familiar with of only one index of refraction, these materials show to the light two indices of refraction, one for one polarization and another one for the orthogonal polarization. And this way, the state of polarization can be changed, and this depends on the wavelength, and this is why we observe this kind of colors in these materials. Okay, what is particularly interesting of liquid crystals is that liquid crystals show these effects. They are anisotropic birefringent materials, but at the same time, these materials show fluidic properties. They can be rotated with the application of a small applied voltage. And this is why they are useful to make this kind of displays, this kind of devices we name LCDs, liquid crystal displays. The interesting point is that you can nowadays have devices where the pixels, instead of being large pixels, and as in the other devices I'm showing in the upper part, they are very small pixels with sizes of few microns, and you can have thousands of them. And you can make a micro screen, what we call a micro display. And this is what is named a spatial light modulator. Okay? And because these pixels are so small, they are capable to produce what we call diffractive optical elements. Optical elements where we control the light through diffraction. Okay? These micro displays have been now used for many different applications, and another trend now in liquid crystal technology is to create what are called pattern retarders or diffractive wave plates or geometric phase elements. These are, again, spatial patterns where you can make pixels, where now what you change is not the phase, as I will explain in a minute, but you change the orientation of the retarders. And this creates another kind of elements which are called geometric phase elements. Okay, but let me go back to the SLMs and start with the optics of the liquid crystal materials. I'm going to talk about, there are many different types of liquid crystal materials, but I'm going to talk about the standard ones. The typical displays use what is called the nematic phase of the liquid crystals. In this nematic phase, the liquid crystals, which are formed typically with long elongated molecules, exhibit this kind of group where the molecules are mostly oriented along one preferential direction. This is called the director of the liquid crystal material. Okay? When they achieve this situation, the liquid crystal material shows optical properties of anisotropy. It means they have one ordinary index of refraction in this direction and one extraordinary index of refraction in the orthogonal direction. This is why it is birefringence. It has two different indices of refraction. In the standard displays that we have been seeing in our devices, what the configuration is what is called the twisted nematic configuration. Here I'm plotting here an illustration where we are seeing one of these devices look from the top. This in the middle would be at the very thin layer of liquid crystal. Here you have the two glasses that protect the two surfaces of the display, and liquid crystals can be oriented in a particular direction over the substrate. So here, in the twisted nematic configuration, the liquid crystal is oriented in one direction. Here is pointing outside the screen, and in the outer surface, the liquid crystal is forced to be oriented orthogonal to the input orientation. This creates the twist structure of the liquid crystal from the input to the output surface of the screen. And this forces the light that's coming here. If we put a polarizer and we polarize the light in this direction, this point, green point here, indicates the electric field of the light coming. This electric field is forced to follow this twist of the liquid crystal material, and at the output, it exits with a polarization which is orthogonal, has rotated 90 degrees compared to the input. Okay? But when an electric field is applied to the electrodes that are placed on the substrates, an electric field is created in this direction, and because of the fluidity property of the liquid crystal, the molecules are forced to tilt in this direction, and the twist structure disappears, and this is why the rotation of the polarization of light that happened in the off situation now is canceled, and the light emerges polarized vertical as the input was. So by simply placing a polarizer at the back, you can see here as a bright pixel, and you can see this one as a dark pixel. This is how these devices that make bright and dark points operate. This is the classical structure for displays, okay? And we have been having this kind of systems in many devices, and the micro displays started when we started to have these projection systems. And these projection systems, we needed to replace the classical slide that we used in the very old times with an electronic display that we can connect to the computer, and the image we have here is projected through the projector device. And this is done by this micro display, these liquid crystal micro displays. Nowadays, the liquid crystal micro displays compete with other displays, which are called digital micromirror devices. In these cases, the pixels are mirrors. These devices are much faster than liquid crystal devices, but on the contrary, they cannot produce direct phase modulation, which is what we are interested in our application. This is why, in our case, we are more interested in liquid crystal devices. Okay, what is the difference when you want to make diffractive optics compared to when you want to make a display? That you don't want to control the intensity, you want to control the phase. In this situation, the kind of configuration of the liquid crystal that is more useful is what is called the parallel aligned nematic display. In this case, what you see is that the liquid crystal is oriented in the same direction in the bottom and in the top. This is why it is called parallel, not twisted. And in this situation, again, when we apply some voltage to the electrodes and the substrate, we align the liquid crystal in this direction, and we get this alignment. And in this situation, the device operates as what we call a linear retarder. For those of you who have studied optics, you are familiar with half-wave plate, a quarter-wave plate. Okay, in these devices, what we are changing is the retardance. What we have here is that with the voltage that we apply, we can control the retardance of this linear retarder. And this is why this is interesting. The retardance is given by the difference of the two refractive indices, and the phase difference between them created is given by this formula. And this has given us devices like this. You can have one single liquid crystal pixel like this that you can use to control the retardance of your retarder, and you can use this to control polarization, or you control the phase in an interferometer, or you can have pixelated devices where you control the phase in each pixel individually, and then you can make diffractive optics. What is diffractive optics, for those of you that don't know? Okay, you are familiar with the classical refractive index, the refractive optics, where you can have a prism, you can have a lens, and through the change of the curvature or change of the shape of the prism, you create, by refraction, effect on the light. Okay, you can do the same if you notice, when you know that the light is a wave, when the wave traverses a material with a given index of refraction, it gains a phase that depends on the index of refraction and depends on the thickness of this layer the light is traversing. So if you can create variations of the thickness, you can mimic the prism by doing, let's call them microprisms, that create the same effect, but only changing the phase instead of continuously as here, they are changing only from 0 to 2 pi. It's like doing modulo 2 pi on the phase that the refractive prism is doing on the light. You can do the same with a lens. In this case, you have what is called a Fresnel lens, because you are changing, you're making the phase of the refractive lens modulo 2 pi. And you have something like this, where you are making phase changes from 0 to 2 pi, and the effect is equivalent to the lens. So this is what we can do with our microdisplays. You can see here a picture that I borrowed from the company HoloEye, where you have a computer, you display these rings, which is the diffractive lens, and these rings are displayed on the microdisplay, and then if we illuminate the microdisplay with a laser, this display will act as a lens. Okay? This is the structure of the device. The liquid crystal material is in this thin layer. The back are the pixels where we control the voltage, and through the reflection of the light, we can control this light beam. These are some of the suppliers that we have nowadays. They are growing. New suppliers are being now in the market. These are the ones that I have been working with in my trajectory. So let me now give you some examples of the things that you can do with these displays. Okay, I mentioned that their main use is diffractive optics. So which is the first element we can consider in diffractive optics? The simplest one. It's a diffraction grating. A diffraction grating can be made simply by making stripes of 2 phase levels periodically distributed all over the screen. You can see here a picture of what we see on the screen. Okay. Here, okay, you can tell me, okay, this is bright and dark, this is not phase. It's because in the microscope we rotated on purpose the polarizer to have a configuration that allows us to visualize the phase changes with intensity changes. When you illuminate this with a laser and you look in the far field, what you obtain is the diffraction orders characteristics from a diffraction grating. In this case, because it's a binary diffraction grating, what we observe is as we change the gray level, we control the phase through the gray level we send from the computer. What we observe is that the relative weight of the diffraction orders changes as the phase is changing. And if you apply standard formulas of Fourier optics, which is given by this gives us the intensity of the 0 order, the central 0 order that you obtain, compared to the plus or minus 1, which are the first 2 lateral orders that you obtain here. This is one of the possible ways you have to characterize, to measure which is the phase difference you're producing in your SLM when you display different gray levels from the computer, because in particular, when the phase is pi, you completely cancel the 0 diffraction orders, okay? However, this image also helps me to illustrate one of the problems that these devices are facing nowadays, which is what we call fringing that cause pixel crosstalk. If we enlarge a little bit the border here between the bright and the 2 regions, you can see one column where it's not completely dark, it's not completely bright. And this is a pixel crosstalk that happens because the voltage that you apply to one pixel affects the neighbor pixel. This is called the fringing effect. This is one of the limitations these devices are facing nowadays, especially because the companies are trying to make devices with smaller and smaller pixels, and as you make the pixels smaller, this effect is more noticeable. Okay, but another important aspect of these devices is that you can have continuous phase. You are not limited to only binary phase. You can make, instead of a binary grating, you can make what is called a blaze grating. You make a continuous change of the phase from 0 to 2 pi, and you make this kind of diffraction grating. In this case, all the energy coming to the SLM, or ideally, will go to the first diffraction order. Instead of doing positive or negative diffraction order, you get all the light going in one direction. This is what you see here. When we have nothing on the screen, you get the 0 order. When you have one blaze grating, all the light is going to the first negative order. If you display the grating in the opposite direction, you get all the light going to the other direction. This is useful to make what is called beam steering devices, devices where you can control a laser and you can move in arbitrary directions, as I can show here. This is a laser that is being controlled by addressing different gratings with different periods and different orientations to the SLM, and we can control arbitrarily the movement of a laser beam. This can be extended. You can create diffraction gratings where you can have arbitrary number of diffraction orders. You can select arbitrarily the location of the diffraction orders. You do this by applying Fourier transform algorithms that give different weights to the Fourier components of the diffraction gratings, and this is what you can obtain. You can also design Fourier transform holograms where you make you get the phase of the target you want to, your laser to become, and you display the phase of the Fourier transform, and the optics does another Fourier transform, and you recover the shape of the laser that you wanted to do. This is called beam shaping, and it's also very useful. I'm showing here some other examples where we make the generation of different laser modes, or the generation of orbital angular momentum modes, which are quite popular nowadays in optics because they create focalization in terms of these donuts of light because they have a singularity of phase in the center. But the fact that we can control the phase of the displays at each pixel give us much more possibilities, not only to stay in diffractive optics. We can use them in interferometry. One of the original uses of liquid crystal devices was interferometry because they can control the phase, and in interferometry, one of the classical techniques is called phase shifting. You have to apply different phases to different paths in the interferometer to obtain the information. Well, the use of SLMs is very interesting to apply in interferometry because, well, you can apply the classical configuration. Here I'm using a laser. We collimate the laser, we illuminate the SLM, and, excuse me, in the SLM, we display the diffraction grating, but one thing that we can do is that we can combine the phase of the diffraction grating with the phase of a lens, and we can create these particular phase holograms, and the combination of the two of them displayed on the SLM produces two effects. It focuses the beam, and in addition, because we have the grating, we obtain the diffraction orders all together. We don't need an external lens, okay? But we can convert this regular standard configuration of using the SLM into our interferometer. The only thing that we need to do is to rotate the input polarizer and keep a second polarizer on the reflected beam. Why we can do this? Because, as I mentioned before, the liquid crystal only changes the phase of the extraordinary index of refraction. It does not change the ordinary index of refraction. So only one polarization of light is being affected by the SLM, only the one which is parallel to the liquid crystal director. If we misalign the input polarizer, we will have some component in vertical direction which is affected by the SLM, and another polarization component in the horizontal direction which is not affected by the SLM. So what happens is that when we do this, instead of having all the light being focused, as it was in the original experiment, we have two beams, one polarized in one direction, which is non-focused, and another one which is polarized in the direction, in this case the horizontal, which is being focused onto the camera. And by placing a second polarizer here, we make the two beams interfere. In general, in optics, two orthogonal polarizations, they don't interfere, but when we put a polarizer and we project both of them to the same direction, we get here the interference. So with this simple system, we have what is called a common path interferometer, which is very interesting because common path interferometers are not sensitive to vibrations of the systems, which is one typical characteristic of many other interferometers. So this is what we did. And in addition, this is one example of what we did. We wanted to reproduce one Hermite-Gauss laser beam by placing a hologram on the SLM. This is the intensity that we will expect. This is the phase of the Hermite-Gauss we will expect. Usually, this is very simple to measure because we only have to measure with the camera. But if we make the configuration of interferometer, we can measure the phase. We can apply phase shifting algorithm by simply adding a constant phase, and we get different interferograms. This is what you see here. This is the intensity image we obtain when we orient the polarizer parallel to the liquid crystal director. Then when we rotate the polarizer, instead of having the intensity, we get interference images. Each of these images corresponds to adding one of these common phase to the whole screen. And from this information, we can measure, we can retrieve the experimental phase that we are generating in the beam. So we can convert very simply the regular standard diffractive optic experiment into an interferometer with this. And we tried this with many different beams. You can see here on top you see the simulations. On bottom you see the experiments. We measure with other Hermite-Gauss beams, also with Laguerre-Gauss beams, which, as I said before, are interesting because the spiral phases create this kind of donuts of beam that increase with the number of runs that the phase does around. We have made very different combinations of different laser beams with different modes to create these spatial patterns that are useful in many in different applications. Okay. I still have some time, so I will now speak a little bit about polarization control. Okay. In polarization control, as I said, we are only controlling one polarization component. We need to control the two polarization components if we want to have a complete control of the polarization. Okay? So this forces us to either to use two SLMs or to make systems where we make light pass 2 times through the SLM. Okay, this is what we did here. I'm not going to enter into the detail, but basically we display one diffraction grating on one side, another in the other side, and by controlling the two SLM, the two screens, the two parts of the screen, we are able to modulate the two components, and we can make, by adding, for instance, in this case, 2 spiral phases, we can create what is called vector modes, vector beams, where the beam shows this kind of polarization. This is called the radial polarization, or these are called the higher order radial polarizations. So, okay, I'm going to go a little bit faster on this. This is showing that when there is no analyzer on the beam, we show the dark point in the center, which is proving the singularity that is being placed in the center. But when you place analyzers on the beam, you can identify that you are creating this kind of effects here. Okay, since I'm running out of time, I apologize, I'm going to skip this part. And I'll go directly to this one. Here, what we did is to apply the same idea, but in combination with gratings. We were able to create a polarization grating together with an OIM grating. So in the horizontal direction, you can see that we are creating different vector modes. The order of the mode is increasing with the horizontal direction, positive and negative. And in the vertical direction, what we are doing is changing the state of polarization of the equivalent analyzer that is analyzing this system. So what we get is different vector modes, and you see that we are producing different vector modes because you see in them different number of lobes, but the orientation of the lobes is changing in the vertical direction while the number of lobes is changing in the horizontal direction. So this is proving that in the horizontal direction we create different orders, in the vertical direction we are mimicking different input polarizations, okay? More recently, we have made vector beams where we are interested not only in making the typical Gaussian vector beam, but to shape the intensity of the vector beam. We use one SLM to create a hologram that makes this intensity distribution, and then we use a second SLM to modify the state of polarization and create that the state of polarization, for instance, in this square, has states of polarization that rotate in the azimuthal direction. Okay. We can also use them to control the spectrum of light. If you use a supercontinuum laser, this is a laser that has all the wavelengths in the laser. You can split chromatically with a diffraction grating, and you can project to the SLM. You can see here a picture of the SLM where the dispersed beam has been projected, and you can apply a different retardance to each of the wavelength, and then the reflected beam is combined again and outputs here. And this way, what you can do is to control the spectrum of the laser beam, and you can see here some examples. We were able to control, you can see here in blue and in red, I'm showing the spectrum. Yes, I finished with this one. And you can see that in one polarization component, you get intensity reflected here, but not in this wavelength, or you can control a spectrum in terms of peaks, or you can control a band of the spectrum that you can generate. So with this, I'm going to conclude because I'm running out of time. And okay, I thank you for your attention, and I will be open to any comments, any questions, or all day I will be here, so you can discuss with me later. Thank you very much.